at this point, we'll now go through an interesting state space example to help illustrate what some of the advantages of using a state space modeling formalism are. So these three equations constitute a state space representation of a physical system. These equations are actually rather famous. They're called the Lorentz equations. They were originally generated as a simplified mathematical model for atmospheric convention. But other physical systems have simplified models of the same form. And so in this case, x, y, and z are the state variables, and sigma, r, and b are constants, or coefficients that represent some physical parameter. So this system is in state space form. Each of these differential equations is a first-order differential equation. The derivative of the one state variable as a function of the other state variables, and so on. Though it's interesting in that it's nonlinear. You'll notice that the equations have these sort of quadratic terms where x is the state variable and y is the state variable, and this is their product. Same thing with here, x times z. So, again, this is something that you can't do with a transfer function. You can't take the Laplace transform of nonlinear differential equations. One of the reasons this is sort of interesting is because this is an example of a chaotic system. And so what that means, what characterizes a chaotic system is a couple things. One, if you change the initial conditions of the system or change the parameters of the system just slightly, you'll get vastly different results. You'll get vastly different behavior. So that's a characteristic of a chaotic system. And the other thing is, if you look at the sort of the time response of this system, for example, if you looked at one of the state variables y as a function of time, it looks very chaotic. It just looks random. Representing the system in state space form, however, gives you a geometric interpretation of the system that can help give you insight. And so this is where the name state space comes from. So what you can do is you can imagine, in this case, we have a system represented by three state variables. And so you can imagine a space with three axes, an x, y, and z axis. And you can sort of look at how the system moves through this state space. So it has sort of a feeling of an object moving along a trajectory through space, but these x, y, and z variables aren't necessarily positions. X could be velocity, y could be voltage, and z could be pressure. But just by sort of looking at how the system moves, how the state of the system moves throughout this state space can give you some real insight into the system's behavior. So since these are nonlinear differential equations, they're challenging, if not impossible, to solve analytically, to solve by hand. And so what we'll do is we'll numerically approximate solutions to these differential equations. That is, we'll simulate them. And so if we look at this, here's the Simulink model of these three coupled equations. This sort of first part represents the first equation. This middle part represents the second equation, and this last part represents the last equation. It looks a little complicated, but it's actually not too bad to generate this model. So if we look at this, x dot is sigma times the quantity y minus x. So here's sigma, this is y, this is x. The difference, you add y, you subtract x, you multiply it by sigma, that gives you x dot. You integrate it once, you get x. So that's where that x comes from. The y comes from down here, the equation for y dot. So y dot is x times the quantity r minus z, or x times r minus x times z minus y. So here, x is branched off, so this is xr, this is x, this is z, so this is x times z, and then this is y being fed back. So xr minus xc minus y is y dot. You integrate it once, you get y. And then the last equation, z dot, is x times y minus b times z. So we branch off x, we branch off y from over here. So this is x times y. And then you feed back z through b. And so x times y minus b times z is z dot. You integrate it once you get z. Okay, so this is a Simulink model of the Lorentz equations. Go ahead and open up that Simulink. Okay, in the workspace, I've defined what sigma, b, and r are. So specifically for this simulation, I'm going to use sigma equals 10, r equals 28, and b equals 8/3. And I've provided initial conditions. An initial condition for x I set in here to be 0. The initial condition for y I set in this integrator to be 1. And the initial condition for z I set to be 0 as well. I'm going to run the simulation. I've forced the time step to be very small in order to slow down how quickly the simulation can run. You can also play with these parameters here. But if I play this, I run this model, the first thing I'm going to do is I'm just going to look at the variable y as a function of time. So I run it. And here is how y is changing as a function of time. We've run the simulation for 100 seconds. And you see this is very chaotic. It just looks completely random. It doesn't appear to be any order in this system at all. You change the parameters slightly, you'll get a really different time trace. However, if we run it again and instead of looking at how the system behaves as a function of time, we look at how the system moves through the state space. So here I'm going to look at x plotted against z. Okay, so again, I'm going to run it. And as it runs, you can see x versus z. It's not random like that time trace was. We get this sort of very pretty sort of, organized plot. They call them butterfly wings, or they call it a figure eight, but really quite organized and interesting. Whereas you wouldn't see this when you just looked at the time trace. So the state space model really can give you some insight. Even when you're dealing with sort of standard, stable, linear systems, you can still get very interesting results. Another name for this is to look at the system in the phase plane, they call it. But you can sort of see if a system is stable and oscillating. You will sort of get a spiraling into the origin. And various things like that. So this state space representation really does provide an interesting perspective. So going back to our slideshow, that sort of completes this example, and it completes this module. So in summary, I'll just quickly sort of discuss the advantages and disadvantages of a state space model, which in essence is a differential equation model or a time domain model as compared to the transfer function model. So some advantages are they are numerically efficient to solve and simulate, including when you get to controller design. You are able to include initial conditions in the model. You are able to model nonlinear and time-varying systems. It's also quite convenient or efficient for MIMO systems with multiple inputs and multiple outputs. And it facilitates a geometric interpretation of a system, like we saw with the Lorentz equations. A drawback is it can be difficult to see the output behavior from inspection. If you just look at the matrices, you can't see what the poles are readily. Though you can determine them from the eigenvalues, but more importantly, you can't see what the zeros are and what the effect of the zeros are, which can be significant. A transfer function model it's not a function of time, it's a function of the Laplace variable s, which can be interpreted as a frequency. Transfer functions are algebraic, so we don't have to deal with derivatives and integrals and things like that, so that's nice. It's easy to connect components, we've seen. When you have components in series, they multiply, or sort of more complicated feedback loops and things like that. You can use frequency response techniques, which have their advantages. However, you can't include initial conditions explicitly, and you can't model nonlinear time-varying systems with a transfer function. So if you have a nonlinear differential equation, you can't take a Laplace transform and put it into transfer function form. Furthermore, each transfer function can only represent a SISO system, single input, single output. You can handle MIMO systems by having multiple transfer functions, but that can get a little cumbersome. So that brings this module to a close.